For question 15, the trolley, when it moved from P to Q, so there is a loss in potential energy. So according to conservation of energy, the loss in potential energy must equal to the gain in kinetic energy, plus here it tells us that there's a work done against the friction. Work done against the friction. Right. So it also tells us that the potential energy at Q is 50 kilojoule less than at P. So directly it is telling us that there is a 50 kilojoule loss of potential energy and there is a 10 kilojoule of work done against friction. So therefore, the change in kinetic energy, which is the gain in kinetic energy, must equal to 50 minus 10, which is 40 kilojoule. So if the kinetic energy at P is 5 kilojoule, then we can calculate the kinetic energy when it is at Q. So since the change is 40, so we say that the kinetic energy final minus kinetic energy initial must be equals to 40. So the kinetic energy final minus the kinetic energy initial, which is 5, equals to 40. Therefore, the kinetic energy final is 45, which is the kinetic energy at point Q. So the answer is B. Question 16. So it tells us that the mass of water flowing per unit time is given 1.5 exponent 5 kilogram per second. We can think of it like this. So we have, let's say, a tube in the form of a cylinder. And we imagine that water flowing out from here. So in 1 second, let's say if we were to observe this point here, so every 1 second, okay, and if we were able to measure the mass of the water flows through, it is equivalent to 1.5 times 10 to the power of 5 kilogram. So that is what it means by the rate of flow of the water. Okay, since when water flows downwards, there's a loss in potential energy. So now we are going to see the rate of loss of the potential energy. Okay, so we know loss in potential energy is simply m, g, and delta h. So the rate of loss of potential energy will then be m, g, delta h over time per unit time divided by the unit of time. Over here we can see that there's a mass per unit time and the g is constant. The delta h is given, it falls through a vertical height of 120 meter. So we substitute this value inside. Mass per unit time is this value, 1.5 times 10 to the power of 5. G is 9.81 and delta H is 120 meter. So this will give us approximately 176.58 megawatt. So this is also the input, it's also called the input power, okay, from the water. So the generator generated 100 megawatt of electrical energy. So this is the output power. So the efficiency is the output power over the input power. So it's 100 megawatt divided by 176.58 megawatt. In percentage, we multiply by 100% to give us 50, round up to 57%. 17. So they want the energy that is not 2400 joule. Right. So the answer is A. Okay, so we look at one by one. We look at B. So the energy transferred in 15 seconds by a machine of power 160 watt. So we use energy equals to power multiplied by time. E equals to PT. You work out this, you will get 2400 joule. The kinetic energy of a mass, this is m, moving at the speed of 20 meters per second. So Ke equals to half mv square. And if you work this out, you get 2400 joule. The work done by a gas expanding against a constant external pressure. So the work done is constant pressure times with delta V, the change in the volume. So P is the constant pressure, 120 kilopascal times 10 to the power of 3. And the change in volume, it increases by this much, so 0.020. So this, if you calculate out, it will also give us 2400 joule. Okay, now the decrease in potential energy, PE, is mg delta H. So when we substitute m as 60, g as 9.81, and delta H is 40 meter, we get approximately 24,000 joule. So that is the answer A, which is not 2,400 joule. Question 18. So we have a train represented by a particle diagram accelerating at A equals to 0.8 meter per second square. There's a resistive force at one instant. There's a resistive force. So the resistive force is 15,000 Newton. So this picture here is a picture at one particular instant of time. So the driving force, we call it F capital D. So using, these are the only horizontal force. Okay, so at this instant, the particle is moving at a speed v equals to 5 meter per second. Newton's law of motion resolving vertically, driving force minus 15,000, which is the backwards force, equals to ma. Net force equals to ma. So we can find what is the driving force. M is 300,000 kilogram. Acceleration is 0.80 meter per second square. The force of resistance, 15,000. So from here, we calculate the Fd to be 255,000 Newton. So at this particular instant, the driving force is this much Newton. The power developed or we call the instantaneous power developed by the engine of the train at that particular instant, P equals to P equals to F, the driving force, multiplied by V. P equals to FV. So that will be equals to 255,000 multiplied by 5 meters per second. And that will give us 1.275 megawatt. So the power developed by the engine, so all these are instant. So at that instant, so the power developed by engine must equals to the kinetic energy. Okay, in this case, we are using the power, so the rate of increase of kinetic energy and also the rate of work done against friction, rate of work done against the friction. So the power developed here is 1.275 megawatt. If I call the rate of increase of kinetic energy as x, and the rate of work done against the friction, so we know the work done is Fd, okay, the force multiplied by the distance it moved. Since the distance is every 5 meters per second, so we take the friction 15,000 Newton multiplied by the speed 5 meters per second. So calculating this, we will get x as 1.2 megawatt. Alright, so which is the answer for B. Question 19. We know the Young modulus E is equals to stress over strain. So stress is F force per unit area over strain. Okay, if we use the increase, that means from a current position, we increase the force, so we will increase the strain. So we are talking about the increase. So the increase in the force, since the area is a constant, and the increase in the strain. So that is the Young modulus. So E times the increase in strain will then be equals to the increase in the force over pi r square. So E is given as 2.5 exponent 11. The change in the strain, which is the increase, 6.0 times 10 to the power of -5. The increase in the force is 34 Newton over pi r square. So we find the r and then square root, and we should get 8.5 times 10 to the power of -4. 20, the area under the path P is the work done to extend the rubber, which becomes the elastic energy stored. So it cannot be these two answers. When it is returned back to where it starts, there's no plastic deformation, and the rubber slipped, the molecule of the rubber slipped, and there's a friction, so energy dissipates.